Welcome to day 3, Chem 2. Today's topic, bond polarity and dipole moment. I do believe you already know what a dipole is. It's basically any molecule where the electrons are not shared 50-50. It's a molecule in which electrons are kind of lopsided. And one example I can give you would be hydrogen fluoride. If I were to go down to the bottom of the page and look at the electronegativities, I believe hydrogen is at 2.1 and fluorine is 4. So remember, electronegativity is the tendency to attract electrons when forming bonds. The electrons are going to spend more time on the fluorine end of the bond and less time on the hydrogen end of the bond. So we can use a symbol, I believe it's lowercase delta, which represents slight or partial. So the fluorine end of the molecule is going to be slightly negative, and the hydrogen end of the molecule is going to be slightly positive. So we can use these little symbols, delta plus, delta minus, to mean slight or partial, or we can use a series of plus symbols and arrows. So hydrogen is going to be the more positive end of the molecule. It gets kind of a plus, and fluorine is more of a negative end of the molecule, so the arrow kind of indicates the direction that electrons travel in, or where they spend most of their time, in this case on the fluorine side of the bond. Another example would be an electrostatic potential diagram. This is just kind of a visual way, a colorful way of looking at dipoles, in which areas that are red are going to be electron rich and areas that are blue are going to be electron poor. So here's 3 examples right here. The first example would be lithium hydride. So lithium would be on the left side of the molecule, hydrogen on the right. I think lithium has an electronegativity of 0.9 or 1, and I know hydrogen is at a 2.1. So the hydrogen end is going to be electron rich, and the lithium end is going to be electron poor. Okay. Another molecule would be H2. Now this molecule is just green because the electrons are shared 50-50. There is no positive or negative end. But then we get to hydrogen fluoride. We know the hydrogen's about a 2 and fluorine's about a 4. So the electrons are going to spend more time on the fluorine end of the bond, fluorine being red and hydrogen being blue. All right, so let's look at some individual molecules. Carbon dioxide. This is one in which carbon would be in the middle. It would be double bonded to 2 oxygens. Carbon has an electronegativity of 2.5, and oxygen is going to be a 3.5. So the electrons are going to spend more time on the far left and far right in red, and less time in the middle, the blue. So we do have polar bonds in carbon dioxide, but because of its geometry, it is not considered a polar molecule. All right, now let's look at water. Water is considered to be a bent molecule. So we've got oxygen in the middle, surrounded by 2 hydrogens. I think the bond angle is about 105 degrees, 104 degrees, and oxygen has an electronegativity of pretty close to, I think it's 3.5. And hydrogen has an electronegativity of 2.1. Notice that both hydrogens are identical, so oxygen gets to spend most of the time with the electrons, and hydrogen gets to spend the least amount of time with electrons. The next one is ammonia, which is a pyramid. So ammonia, guys, is kind of hard to see because those hydrogens are hiding behind, but you've got a nitrogen kind of in the upper right-hand corner. You've got surrounded by 3 hydrogens, and keep in mind that nitrogen is going to have an unshared pair on it. Nitrogen, I believe, has an electronegativity of 2.5 and hydrogen a 2.1, and those electrons are going to spend much more time on the nitrogen end of the bond than the hydrogen end. So the nitrogen end also has an unshared pair sitting on top, and if I zoom out a little bit, you guys can see where they spend most of their electrons. All right, I'm not going to spend too much time talking about hydrogen chloride. Very, very similar to hydrogen fluoride. Keep in mind, hydrogen is at about a 2.1. I think chlorine is a 3.0. So they're going to spend most of their time on the chlorine side of the bond. All right, let's take a look at Cl2. Very similar to H2 in that we have a molecule where both atoms have the same electronegativity. So there is no polar bonds, and because of that, we don't really use colors. I think in the hydrogen example, it was all green. This one's all gray. But because this is a nonpolar bond, it is also a nonpolar molecule. All right, next one is sulfur trioxide. Sulfur has an electronegativity of 2.5. Oxygen has an electronegativity of 3.5, so we do have polar bonds, but because of its symmetry in this case, these three bonds kind of cancel each other out, and as a result, there is no dipole moment. Last example is going to be, two more examples. We've got methane, which is a tetrahedron, kind of hard to draw a tetrahedron, but you've got carbon in the middle surrounded by four hydrogens, hydrogen being a 2.1 and carbon being a 2.5. So these are slightly polar bonds, but because of its symmetry, we have no dipole moment, and as a result, really, we're not going to get a polar molecule. Last one, hydrogen sulfide or dihydrogen sulfide, very similar to water in that we do have a bent molecule, sulfur in the middle, surrounded by two hydrogens. Sulfur has an electronegativity of 2.5 and hydrogen of 2.1. So because of its bent geometry and slightly polar bonds, this does have a dipole moment. Remember, if you guys have questions, contact me through email or leave a comment. Also, miss you guys, love you, stay healthy, and see you soon.